times.
What is it? 16. Okay? Beyond that, further elongation, and if necessary, desaturation, where do those occur? Can you see around Nikki's water bottle?
More or less.
Okay. Where do those occur? When in doubt, what are you supposed to guess when you're guessing subcellular locations for odd events?
The liver.
No, the liver is the organ you guess.
Oh.
If you're within a cell.
Mitochondria.
No.
Cytoplasm.
No.
11.
No.
Membrane.
No. What membrane?
The intermitochondrial membrane.
No. Lots of weird stuff happens here. When in doubt, guess this. Right?
Lysosome.
No. When in doubt, guess endoplasmic reticulum.
I don't think you've ever told us that.
Huh?
You said that like 6 times and you said no.
No, nobody said endoplasmic reticulum. At least not loud enough that I could hear it. I get a lot of mumbling. Remember, I'm aged. You have to talk loudly and clearly for me to hear it.
No.
No, they kept saying mitochondrion and... Right?
We were wrong.
So, right? So that continues. We get 7 reaction cycles to get the palmitoyl acyl protein. When you get the palmitate, the thioester is hydrolyzed, that is released as palmitate. Any further elongation and desaturation occurs in the endoplasmic reticulum.
Are we going to talk about how that occurs?
We're going to talk a little bit about how it occurs. Depends on how it's going. I'm running out of time, though.
Is there a reason why it can't all be done in one place?
I don't know what the reasoning, the metabolic reasoning is for stopping at 16 and moving to other processes beyond 16. Let's see.
So is there a special transporter for that to get it out then?
No.
Or in, sorry.
Well, it's a lipid. I don't know how those lipids get into the endoplasmic reticulum. There has to be a way because they do. But I don't know what it is.
Maybe that's why they stopped there, because that's the only one that has a transporter.
Yeah. So this is a layout of the peptide of the fatty acid synthase complex. Right? It's sort of a complex thing, right? So this is the acyl carrier protein part. This is the ketoacyl reductase. This is the dehydrogenase. This is responsible for interaction of the dimers with each other. This is the ketoacyl synthase. What's MAT? The malonyl the malonyl transferase. Yeah. So let's see. I like this. What's this? It's triclosan. What is it?
An antibacterial agent that inhibits bacteria.
Yeah. In bacteria, I hate it when I give away the ending. In bacteria, instead of these things being all part of one large multi-enzyme complex, they're distinct enzymes. And so you can inhibit, right, since they're not coordinated in the same way they are in mammalian systems, you can individually inhibit the different processes. So the stuff like in the antibacterial soaps is this stuff, right? And it inhibits the ability of bacteria to carry on fatty acid synthesis. That's the way it works. Okay, now, the desaturation problem, right? So, in the fatty acid desaturases found where, Reed?
Endoplasmic reticulum.
Thank you. in the endoplasmic reticulum are NADH requiring oxidases, right? You're using oxygen as the direct oxidant, and then you tend to get peroxides. You use NADH to reduce the peroxides. Okay? So because we don't have the carbonyl to help in putting these double bonds out in the chain, we have to use a much different system than we did when we were making double bonds close to the carbonyl. Okay? So these tend to be cytochrome requiring enzymes in the endoplasmic reticulum membrane, right? That create cis double bonds within the chain. Right? Remember, natural double bonds in fatty acids are cis. Okay, now, in mammalian systems, we're good. We can put double bonds after carbon 4, 5, 6, and 9. But we don't have enzymes to put double bonds farther out than 9. Right? That's a problem. Right? Now, it's a problem in part because if you think, what was one of our important fatty acids was arachidonic acid. And it was what? Delta 9, 12, 15? Is that right? Did I get that right?
Doesn't it have 4?
Yeah, I thought I had 15.
15, 18? 9, 12, 15, 18? Right? That's a problem. Or just 12, 15, 18? I can't remember. Right? I can't remember. Right? But this important fatty acid has double bonds out at the far end of the chain, and we only have desaturases that will put double bonds in the near half of the chain. Right? So, what was one of our essential amino acids?
Linoleic.
Linoleic. And why did we say linoleic was essential? What could we make out of from linoleic? What we just talked about.
Arachidonic.
Arachidonic, right? So linoleic is essential because it is a fatty acid that already has double bonds out at the far end of the chain. So we can take the 18 carbon linoleic and use our endoplasmic reticulum elongation system, which chemically follows along the same pattern. And the desaturases we have to convert linoleic into arachidonic.
How is linoleic made then if it's 18?
That's why we have to get it from plant sources. Plants have desaturases that will make that. So we get linoleic from our diet, and then we can convert it into arachidonic because we have the enzymes that can put the nearer double bonds and lengthen the chain. Right? So that explains what we said in the first semester about what fatty acids are essential.
What do we use arachidonic for again?
What do we use? Who are my immunologists?
We didn't talk about that in immunology.
Huh?
We didn't talk about arachidonic in immunology.
You didn't talk about thromboxanes and leukotrienes and...
Not really, no.
Yeah.
Not really? Okay, what's my question going to be?
What are they teaching you?
Yes, thank you. Right? Oh, we're out of time. So now we're going to jump to cholesterol synthesis, I believe, here pretty quickly. Let's just commit to that. Let's go directly to, we're going to jump over phospholipid stuff. We're going to go straight to cholesterol. There's a lot of cool stuff there, right? There's our arachidonic, right? There's why arachidonic is. Right? But we're just going to go right to cholesterol because everybody wants to talk about cholesterol. We'll talk about cholesterol Monday, Tuesday, hopefully I can